Welcome to the incredible world of Formula Student Electric. This is where university teams from all over the globe design, build, and race their very own cars. But listen, this is so much more than a university project. It's really a crucible for the world's next generation of top engineers. So today, we're going to pull back the curtain and look at the professional playbook, the exact strategies I've seen the very best teams use to engineer success right from day one.
So that brings up the big question, right? How is this even possible? We're talking about building a machine that's not just insanely fast, but also has to be incredibly safe. And it's all built from scratch on a student's schedule with a student's budget. Well, that is the central puzzle, and the answer, you'll see, lies in the engineering strategy, the thing that separates the winners from the teams that honestly never even make it to the starting line.
And let's be real, the scale of this challenge is just immense. First off, you're dealing with a high-voltage system that is, and I'm not kidding, literally lethal if you mess it up. The competition is global, and it is ferocious. You're up against teams with decades of experience. You've got an 18-month deadline, starting from a totally blank sheet of paper. And the whole thing is governed by a rulebook so strict, so unforgiving, that being off by a single millimeter can get you disqualified. Your whole season's work, just gone.
Now, when you're faced with that kind of pressure, teams usually go down one of two paths. There's what I call the old way. It's this chaotic cycle of just designing something, building it, and then desperately trying to fix all the flaws you find on the racetrack. It's super high risk, it's unpredictable, and frankly, it often ends in failure. But then there's the professional way. This is a systematic, controlled process where success isn't just something you hope for, it's something you engineer right from the beginning.
And that professional way is built around this one powerful idea, the V model. You should think of it as the strategic playbook for any complex engineering project. It's a framework that forces you to connect every single design decision you make on the left side of this V with a specific test on the right side to prove that it actually works. It's how you tame the chaos and build with genuine confidence.
And if you want to know the entire strategic value of this model, it really boils down to this one concept: risk shift left. This is the core philosophy. Instead of waiting around to find problems out on the racetrack, where they're dangerous and incredibly expensive, you actively hunt for them as early as you possibly can, on the computer, back in the design phase.
And this right here, this brilliantly shows why that is so important. The cost to fix a design flaw that you find during track testing can be over 100 times more than fixing that exact same flaw in the early digital design phase. I mean, think about it. Finding a software bug on your laptop costs maybe a few hours of coding. Finding that same bug when the car fails at 120 kilometers per hour, well, that could cost you the entire car.
Okay, so let's take a walk down the left side of the V. It all starts with the System Requirements Review, or SRR. That's basically where the team pores over the rulebook to figure out what fast actually means in hard numbers. Next up, you've got the Concept Design Review, or CODR. This is where you make the big architectural choices. From there, it's the Preliminary Design Review, or PDR, to figure out how all the different pieces are going to fit together before you finalize every last bolt and wire in the Critical Design Review, the CDR.
And here's a perfect real-world example of how the V model guides a huge concept decision. Let's take the powertrain. A four-wheel drive system with hub motors? Yeah, that offers the ultimate performance, but the complexity and the risk for a brand new team are just extreme. The V model forces you to make a strategic choice, and it guides a new team toward a simpler single-motor design. It might not be the fastest car on paper, but it is the one that's most likely to actually succeed in reality.
So now we arrive at the very bottom of the V. This is the turning point. After months and months of digital design, of simulation, of review, the team's digital twin is finally approved. The designs are locked in, and for the very first time, manufacturing begins. The digital blueprint is finally transformed into real physical parts.
And now we start to climb up the right side of the V, which I like to call the gauntlet. This is where every single design choice we made going down the left side is put to the test. The whole goal here is to prove the design works, piece by piece, long before that car ever hits a real racetrack.
And a key secret weapon in this phase is something called hardware-in-the-loop testing, or HIL. You can think of it like a flight simulator, but for the car's electronics. You take the car's actual controller, its brain, and you plug it into a powerful computer that pretends to be the rest of the car. It simulates the battery, the motors, the wheels, even a virtual racetrack.
And this is the real magic of HIL. While the chassis is still being welded together, while the battery is still being assembled, the controls team is already running virtual laps, debugging software, and fine-tuning the car's performance. They are literally testing the car's brain before its body has even been born.
But the true power of HAL is testing for failure. You can safely simulate all these catastrophic events that would be absolutely impossible or incredibly dangerous to test on a real track. What happens if the accelerator pedal sensor fails mid-corner? Or what if a communication line just crashes? With HAL, you find out, you fix the software, and you end up building a car that is resilient by design.
So after all of this, all the virtual testing, all the component-level testing, the fully assembled car has to face its final exam, scrutineering. This is a series of intense physical inspections where veteran judges from the auto industry meticulously check every single aspect of your car to make sure it follows the rules and, most importantly, that it's safe to race.
The gauntlet kicks off with the rain test. And for an electric car, this is basically a controlled nightmare. The car gets blasted with water while its high-voltage system is fully powered up. A single drop of water in the wrong place could cause a catastrophic short circuit. Passing this test is a direct validation of hundreds of tiny decisions you made about seals, enclosures, and connectors months ago.
Next up, the tilt test. The car is hoisted onto a platform and tilted to this crazy 60-degree angle. They're checking for two things. One, that no fluids like coolant or brake fluid leak out, and two, that the car is fundamentally stable and won't just roll over. This proves that your core mechanical packaging and your center of gravity calculations, the ones you did on a computer 6 months ago, were actually right.
And finally, the brake test. This is a big one. The driver has to accelerate and then slam on the brakes hard enough to lock all 4 wheels solid. This proves, in the most visceral way possible, that the mechanical braking system can always overpower the electric powertrain, and that's a critical, non-negotiable safety rule.
So, after surviving the design reviews, the manufacturing, the virtual testing, and that brutal scrutineering gauntlet, we have to ask ourselves, what's the real measure of success here? What is the true victory lap?
Well, it really brings us to the hierarchy of success in any kind of motorsport. Raw speed? Sure, that's important. Clever design? Yeah, that's very important. But the foundation, the thing that everything else is built on, is reliability. A brilliantly designed car that breaks down gets 0 points, and reliability isn't luck. It is the direct outcome of a disciplined, professional process.
Which all comes back to the oldest and wisest saying in all of motorsport. It's the core philosophy that underpins this entire V model. The goal isn't just to build the fastest car, it's to build a car that can actually survive the race. Because to finish first, you must first finish.
And that kind of leaves us with a final thought. This disciplined, simulation-first approach, this V model, is incredibly effective at building a complex race car under immense pressure. So what if we applied that same kind of thinking to the other complex challenges we face out there in the world? What else could we engineer for success?